which seems pretty good. How many of you got this done? Like, you were able to come up with the right answers for this problem? Anyone? Yeah, it's 27, so it's odd, so there was answers? No? Okay, well then, good. All right, so Gauss's law tells us that the flux caused by any given amount of charge, right, is equal to the kind of like the is equal to sort of the diffusion or the density of the electric field times the area through which that we're observing that electric field. That's what it's saying, right? And it's saying that all of that is a function of charge inside if you're using a true Gaussian surface. Without this is just the definition of flux. Does that make sense to you? With this is Gauss's law, because now it's talking about like electric fields caused by this contained charge. Sorry, I should put that. Okay. Luckily, in this situation, we have a nice spherical symmetry here, so we can we can say this is going to use Gauss's law. All right. So let's say, all right, this electric field is constant as given in the problem. Also, we know that the area of perfusion, the area in question, is a given value. Does that make sense? Right? Because when we integrate over the surface of a sphere, we're just going to get the full surface area of the sphere. So what we get is that this flux is going to be this E value times the whatever 4 pi r squared of that sphere. And then that's going to equal Q over E0. Oh, you know what? As an aside about the class, I didn't flip the class at the semester. I usually do. Like, I usually flip the whole class. Wait, did I do that?
No.
Okay.
I already did it.
So, is there, like, do people want to stay where you are, or do you want to be flipped? Because for all of you guys, I just stand here and talk, and you kind of like have to listen and look up there, and look at me and look up there. So, how many of you would like to rearrange a situation? Would anyone like to change seats? Jackie's like, no. Okay, where the heck is he? So, who would like to change seats? Please feel free to say if you'd like to change seats, raise your hand. Okay, anybody who wants to change seats, you have priority to sit wherever you want. So, totally serious. And that priority, the priority will go according to those stuck on the seats back there, and then on this side of the room going this way. Okay, clearly they're not moving. It's fine.
So if you move, someone else will you.
This isn't a white elephant give big change. Does anybody want to move? Tina, did you want to move? What's that? You sure? I can move both you and Sophia if you want. I don't know, she can look. You're fine? Okay, I just wanted to say that because, yeah, without, even with the iPads, I tend to stand over here. I don't know why. Even when I was doing it on the iPad, it's like,
once in a while you get hitting it was really bad at the beginning.
So McClure, if you got that board, like if you got another one and put it right there, would you go there?
I've thought about it, but like I'd have to get this board's like $1,100, and then I don't think you can have two of them on the same system at the same time.
Oh.
What? No, because like was it last? Did you have my people in my class last year? Remember that TV? Yeah, there was a TV over here, and then I could just. Oh, I see what you're saying because I can stand like this and talk, but. But I mean, I think I lectured from over here several times. Yeah. No, it was when the TV was there. So it's like if I don't have something to write on, then I come over here and go like this, and crap, and then I gotta walk back over there. So. And then I'm gonna try to bring in my Apple TV and switch it up so I can go back to the iPad.
Technology.
We'll see who's out here.
Oh, I name is because I was over there and then the team and I come back here. Where are you?
Oh, you mean you want me to move you back there? He's there.
And you.
Okay. Anybody absent besides Abby? Oh. What's that? Don't do it. Is that it?
Yeah, it's good.
Anybody else? All right. We're good. Okay. Whoops. Yeah, I take care. Oh yeah. This is the last year of honors.
What?
Yeah, there will be no more honors after this year. No, there will be one AP, and then there will be regular, and regular will have an optional AP test. Because they took the honors. What is essentially AP Physics B, and they cut it in half. And then that thing they cut in half is mech, a tiny bit of thermo, E&M, and that's it. Yeah, I know. But that's pretty much what we did in regular. Mech, a little bit of thermo, and E&M. So I'm just going to teach regular, and then if you want, like, you'll take extra, like, when everybody takes a regular test, you'll have an AP question.
Will it be weighted?
No, see, that's the thing. It won't be weighted.
Then no
The
one
only
can
thing
do
that
it.
will happen is it'll prepare you for the AP test. That's it. See, the issue is, what I'm going to try to think of is, I want to see how many people will do it. And if people will do it without it being weighted, then I'm going to get approved to teach AP1, and then it will actually be that the next year. So you have to sign a contract in September. Like maybe like by the beginning of September that says that you are in AP Physics. And if you do that, then you have to take AP tests and you have to do all that stuff. But then you would actually get the extra points. So. Okay, anyways. Oh my gosh. All right, anyways, nothing interesting. I think it was just a discussion about desks or whatever. But anyways, so does this make sense? So then we can just say E is equal to Q over 4 pi E0 R squared. Does that look familiar? It's KQ over R squared, right? So that is this. Now, of course, we're supposed to find, oh yeah, we're supposed to find Q. So, we shouldn't solve it. We should solve for this. Q is E 4 pi R squared E0. Well, this Q is just Q inside. We don't know, like, yeah, so good point. Hang on one second. So does this make sense? Okay, so this tells us that is the total amount of charge enclosed by everything. That doesn't tell us how much charge is on this surface or that surface or anything. So we got to explore a little bit more. Now I'm going to pick, and why did I choose this point to put my Gaussian surface on. It's outside all the charge. It puts everything inside. What else? What's that? Question? Anyone? True. I know that specific distance. Anything else? The important thing is I need to know the actual electric field strength. Right? I can't do this calculation if I don't know the electric field strength. Right? This and this are mutually exclusive. You're either going to be given the field strength and you come up with the charge, or you're going to be given the charge and you come up with the field strength. Does that make sense? The radius is incidental. You have to know that, but you know. Okay, so now I'm going to go to this one because I know how much charge is enclosed by this. So if I now can find the charge enclosed by this, I can just subtract. Does that make sense? Okay, so we can do that again. Same idea. The charge inside that is going to be the electric field strength there, 4 pi r squared E0. That's going to give me the amount of charge on this interior sphere. And then, as per our discussion at the very end of class the other day, if I put, and which way is that electric field going? Yeah, in. Therefore, this must be out. Yes, this must be. This goes up. That must go sideways. No, okay, so this is going to be negative. So this is negative charge inside. And as per that discussion, if I have this charge in here that's negative, what has to happen here? Positive. Now, this is the, okay, I'm going to pause this for a second.